We are currently engaged in a brief exploration of our connection to the vast Andromeda Galaxy, which contains a couple of 100 billion stars. This impending collision will trigger a significant transformation, affecting both galaxies in profound ways. Andromeda, which has played a crucial role in demonstrating that the universe does not revolve around us, has been the focal point of astronomical study for over a century. It was Andromeda that revealed the Milky Way was not the only galaxy, fundamentally altering our understanding of the cosmos. For more than a century, advancements in technology, such as the James Webb Space Telescope, have provided astonishing insights into Andromeda that were previously unimaginable. Just over 100 years ago, the Milky Way was perceived as a faint band of light in the night sky, obscured by the limitations of contemporary science, which hindered the understanding of individual stars. Various theories about the Milky Way positioned it at the center of creation. This perception shifted in the mid-17th century when Galileo Galilei used his telescope to discover that the Milky Way was not just a cloud of light but a vast collection of stars, planets, and celestial objects. Galileo's findings laid the groundwork for the understanding that the Milky Way was a sprawling expanse of stars. In 1750, the English astronomer Thomas Wright hypothesized that the Milky Way was a flat disk of stars, including our solar system, although this idea was limited by the scientific knowledge of his time. By the early 1900s, significant progress had been made in cosmology. In the 1920s, Edwin Hubble utilized the 100-inch telescope at Mount Wilson Observatory to demonstrate that distant nebulae, including the Andromeda Galaxy, were actually separate galaxies containing billions of stars, fundamentally reshaping our understanding of the universe. The Andromeda Galaxy, also known as M31, has been observed since at least the 10th century when the Persian astronomer Abd al-Rahman al-Sufi described it as a little cloud. His keen eyesight allowed him to identify Andromeda without the aid of telescopes, a remarkable feat since Andromeda is one of the few galaxies visible from Earth's surface without advanced instruments. It wasn't until 1612 that Simon Marius provided a detailed account, establishing a foundation for future astronomers. In 1764, Charles Messier classified Andromeda as M31, further solidifying its recognition. A major breakthrough in understanding Andromeda occurred in 1864 when the English astronomer William Huggins analyzed its spectrum, revealing it to be distinct from typical gaseous clouds, a crucial realization. Andromeda is massive, with an estimated mass ranging from 1 to 2 trillion times that of our Sun and is believed to be nearly 10 billion years old, indicating a complex history of evolution through the merger of smaller protogalaxies. Initially, cosmologists thought Andromeda was significantly larger than the Milky Way, but later research revealed that the two galaxies are much closer in size than previously thought. The actual dimensions of the Andromeda Galaxy are greater than those of the Milky Way, measuring approximately 220,000 light-years in diameter compared to the Milky Way's 100,000 to 175,000 light-years, highlighting its vastness. One of the intriguing features of Andromeda is its active galactic nucleus, powered by a supermassive black hole with a mass between 110 to 230 million times that of our Sun. Observations from advanced telescopes like the Hubble Space Telescope have revealed two focal points of interest within Andromeda, with the brighter one slightly offset from the central supermassive black hole, indicating complex gravitational interactions and the presence of a very large black hole. Andromeda also hosts an abundance of globular clusters, estimated at around 460, each containing thousands to millions of stars. This abundance reflects Andromeda's history of galactic violence, where smaller systems were absorbed into Andromeda, contributing to its stellar population and diversity. Current observations suggest that Andromeda may be transitioning from a spiral galaxy to a ring galaxy, a relatively rare type characterized by circular ring-like structures of bright young stars. These ring systems can form through galactic interactions or when a smaller galaxy passes through the center of a larger one, making them fascinating among astronomical structures. The impending collision between the Milky Way and Andromeda is a monumental event projected to commence around 4 billion years from now, unfolding over the next 2 billion years. This grand event will culminate in the formation of a new supergalaxy, informally dubbed Milkdromeda by astronomers and enthusiasts. The merging process will be marked by significant gravitational interactions and tidal forces that will drastically affect both galaxies. As the Milky Way and Andromeda draw closer, their immense gravitational forces will begin to distort each other's shapes. This gravitational interaction will pull stars, gas, and dust from each galaxy, creating elongated tidal streams and triggering a series of complex gravitational interactions. The merger will not be a smooth process but rather characterized by turbulent and dynamic changes as the galaxy's structures are gradually disrupted and transformed. One of the most spectacular outcomes of this collision will be the formation of new star clusters. As the galaxies collide, the gas clouds within them will compress and collide, leading to bursts of star formation. These stellar nurseries will be regions where strong gravitational forces compress gas to the point of collapse, resulting in the birth of new stars. These newly formed stars will often group together into clusters, contributing to the new supergalaxies' stellar populations. Simultaneously, the gravitational disturbances will alter the orbits of existing stars, which had previously been in stable orbits around the centers of the Milky Way or Andromeda. Many will be thrown into new, more eccentric orbits or may even be ejected from the merging system altogether, becoming rogue stars that are no longer bound to any galaxy. This redistribution of stellar material will contribute to the development of new galactic structures and could result in an intricate web of star streams and clusters that blend the remnants of both galaxies while simultaneously forming new stars and clusters. The merging process will also create large-scale structures within the new galaxy. The gas, dust, and cosmic debris from both galaxies will intermingle and settle into new configurations, forming vast regions of star formation, spiral arms, and potentially new galactic features that are hybrids of both the Milky Way's and Andromeda's original structures. These structures will evolve over time, influenced by the new dynamics of the combined galaxy. At the centers of the Milky Way and Andromeda will play a critical role in this merger. As the galaxies coalesce, their central black holes will eventually merge, creating an even larger supermassive black hole at the center of Milkdromeda. This newly formed black hole will serve as a powerful source of energy and will significantly influence the surrounding cosmic environment, contributing to the new galaxy's dynamics and active features. Ultimately, the merger of the Milky Way and Andromeda will lead to a completely transformed galactic landscape. The new supergalaxy Milkdromeda will be a significant entity formed from the merger of these two massive systems. The upcoming merger of the Milky Way and Andromeda galaxies will create a stunning tapestry of new star clusters, redesigned celestial circles, and reformed cosmic structures. This monumental event, driven by gravitational interactions and consolidation, will profoundly impact the fate of our local group of galaxies and provide unique insights into the long-term dynamics of cosmic interactions. As these galaxies collide, expected to occur in about 4 billion years, our night sky will undergo significant transformations, altering Earth's climate and potentially affecting ecosystems, biodiversity, and biomes. However, these changes will occur long after humanity has vanished, as our sun will evolve into a red giant, rendering our solar system uninhabitable in roughly 5 billion years. The merger will raise questions about our solar system's future and the formation of new cosmic structures. It will likely create an environment with habitable zones for life, albeit vastly different from what we know today. This new cosmic landscape, known as the Milky Way-Andromeda system, will exemplify the universe's dynamic and ever-changing nature. The gravitational dance between the Milky Way and Andromeda has been ongoing for billions of years, and as they approach each other, one of the main expected outcomes is the transformation of their spiral structures. Currently, both galaxies feature distinct spiral arms that extend outward from their central bulges, shaped by the rotation of stars and gas. As they near one another, the gravitational forces will distort these spirals, stretching and elongating their arms into extended, flowing shapes composed of stars, gas, and dust drawn from their original orbits. This will create a mesmerizing display across the cosmic landscape. The merger will also trigger intense bursts of star formation in the newly forming supergalaxy. The interaction between gas clouds from both galaxies will compress and heat up, leading to the creation of massive luminous star clusters that will act as nurseries for new stars. Their radiant energy will illuminate the surrounding cosmic dust and gas, resulting in vibrant new stellar populations. In addition to altering the galaxy's appearances, the merger will significantly impact their internal dynamics. Gravitational interactions among stars and gas clouds will cause a redistribution of their orbits and velocities. Some stars may be thrown into erratic orbits, while others could be ejected from the merging system altogether, becoming rogue stars drifting in intergalactic space. At the centers of both the Milky Way and Andromeda lie supermassive black holes, which will play a crucial role in shaping the future of the newly formed galaxy. Each of these black holes is millions of times more massive than our Sun and will ultimately spiral toward one another, influenced by the gravitational waves emitted as they get closer. The final phases of this merger will unleash tremendous energy into space in the form of gravitational waves and radiation, ultimately forming a single, much larger supermassive black hole at the heart of the new galaxy, surrounded by a swirling accretion disk of gas and dust. The presence of this powerful central engine will have significant implications for star formation within the supergalaxy, influencing the behavior of gas and dust in the galactic core. It could also lead to quasar-like phenomena as material falls into the black hole, emitting intense radiation across the electromagnetic spectrum. On a larger scale, the merger of the Milky Way and Andromeda will contribute to the ongoing evolution of cosmic structures in the universe. Galaxy mergers and interactions are essential processes in the hierarchical model of galaxy formation, where smaller structures combine to create larger, more complex systems over vast timescales. Studying significant cosmic collisions like that of the Milky Way and Andromeda offers astronomers valuable insights into the mechanisms driving galaxy evolution. The merger will also have implications for the distribution of dark matter within the newly formed supergalaxy. Dark matter, an invisible and elusive form of matter that makes up a substantial portion of the universe's mass, plays a critical role in shaping the structure of galaxies and their gravitational interactions. During the merger, the gravitational forces exerted by the dark matter halos surrounding the Milky Way and Andromeda will interact and merge, influencing the overall distribution of dark matter in the new galaxy. Observing the effects of dark matter during and after the merger will provide crucial insights into its nature and properties, helping astronomers unravel some of the biggest mysteries in modern cosmology. Additionally, this merger will present a unique opportunity to study the formation of galaxy groups and superclusters, massive structures made up of numerous galaxies bound together by gravity. These are the largest known structures in the universe and hold clues about the large-scale distribution of matter and the formation of cosmic web-like structures. As the Milky Way and Andromeda merge, they will bring their respective satellite galaxies along for the ride. These smaller galaxies, orbiting their larger counterparts, will be gravitationally integrated into the merging process, either merging with a new supergalaxy or being disrupted and absorbed into its extensive halo of stars and gas. The fate of these satellite galaxies will depend on their orbits and velocities relative to the merging Milky Way-Andromeda system. Some may survive the merger relatively intact, becoming dwarf galaxies within the new supergalaxy, while others may be disrupted and ultimately consumed. Although the direct impact of this merger will not pose an immediate threat to Earth, the gravitational disturbances and influx of astronomical radiation from the merging galaxies could subtly affect our planet's climate and cosmic ray exposure over geological timescales. Moreover, the formation of the new supergalaxy will result in a dramatically altered night sky for any future inhabitants of the Milky Way. The merger will reshape the positions and distributions of stars, star clusters, and nebulae, potentially creating new star formations and celestial landmarks that will influence the culture and navigation of any civilizations that arise in the distant future. In summary, the merger of the Milky Way and Andromeda presents a cosmic spectacle on an unimaginable scale. It will reshape both galaxies into a new supergalaxy, integrating the materials and characteristics of their progenitors into a unified cosmic entity. From the transformation of spiral arms and the formation of new star clusters to the merging of supermassive black holes and the rearrangement of dark matter, every aspect of this merger will leave a lasting imprint on the future evolution of our local group of galaxies. This event offers astronomers a rare opportunity to witness the profound influence of gravitational interactions in shaping the universe we inhabit, showcasing the dynamic and ever-changing nature of cosmic evolution, where galaxies collide and ultimately give rise to new structures and phenomena that continue to inspire wonder and curiosity about the cosmos.